Mr. Russell, and we're here to talk about the mole. These slides are designed for AP Chemistry. The first 7 slides are a review from what you learned in first year chemistry. So the mole is exactly defined as the number of carbon atoms in 12 grams of pure carbon-12. They chose the isotope carbon-12 because it's stable, and they chose carbon because it's abundant all throughout the Earth. Remember Avogadro's number, 6.02 times 10 to the 23rd, and also remember that the molar mass is down at are the numbers below the element symbol on the periodic table. Remember that the molar mass is exactly the number of grams that are in 1 mole of that substance. Let's get a warm-up problem in here. If Cody found a gold nugget that had a mass of 1.250 ounces, how many moles was this? How many atoms? Notice that the extra information here is provided for you, so you'll need conversion factors. The AP test is not in the habit of giving you extra information. Everything that is in the problem is almost always designed for that question. So that is a good thing, right? So we'll have to use our railroad tracks, start with our ounces of gold, and we'll convert ounces to pounds, pounds to grams, and then grams to moles. When we type that into the calculator, we take the product of everything on top and we divide it by the product of everything on bottom, and we will get our final answer of 0.799 moles. Remember, our answer had 4 sig figs here, and that's because we started with 4 sig figs here. These are exact numbers. These are exact conversions, so that means that they have an infinite number of significant figures, and we kind of exclude those. When we then convert moles into atoms, we'll use our dimensional analysis again to go from moles to Avogadro's number of atoms. That's how many atoms are in 1 mole. Remember A for Avogadro's number, A for atoms. And we'll get this final calculation. This answer does make sense because if you had a gold nugget, you would have an obscene amount of atoms in that gold nugget. We'd have a very, very large number, so that makes sense. If we were to calculate the molecular mass of cisplatin, this will happen a lot, where you'll get a molecule you've never heard of the name, but they provide the formula. So to find the molecular mass, we'll take 1 platinum, there's 1 platinum here, and we'll add it to the mass of 2 nitrogens. Notice there's 2 nitrogens, mass of 6 hydrogens, and the mass of 2 chlorines. We'll add those all together and we'll get our total molar mass of 300.06 grams. Notice that here are significant figures. We're not, because we're adding here, we're going to take the number of decimal places since we're adding, not 3 sig figs like you would do with multiplication. You need to keep the same number of decimal places. Remember, the molecular mass is the same, or is also known as molar mass, molecular weight, and formula mass. How many grams are 3.25 moles of cisplatin? So we'll take the molar mass, or the molecular mass before, and we will now apply our railroad tracks to go from moles of cisplatin to moles 2 grams of cisplatin. And it's perfectly acceptable to use these as your units instead of actually writing the full out molecule. Sometimes it's easier to write something like that. And we'll type that into our calculator and we'll get 3 sig figs for our final answer. The percent composition is known as the mass percent or percent by mass. You will take the total mass of the element and divide it by the total mass of the compound. This will give you a decimal place, and we will multiply by 100 to create a percentage. To find the percent composition of cisplatin, what we've been using before, we will need to identify how many elements are in there. There are 4 of them: platinum, nitrogen, hydrogen, and chlorine. So we will take the numbers of, we'll take platinum and take the molar mass of platinum and divide it by the total molar mass, which we found before, 300.06, and multiply it by 100 to get 65.01%. We'll do this likewise for the next few terms, and we will get, I'm waiting for this to go away, and we will get all of our percentages. Notice that the numbers in red will should add up to 100%. If it doesn't add up to exactly 100%, that's probably due to some rounding error, and that is acceptable if you get within about a tenth of a place. So if you get between 99.9% and 100.1%, those will be acceptable. We'll have to get a better understanding of determining the formula of a compound. To do this, we must know the difference between a molecular formula and an empirical formula. A molecular formula is the exact formula of a molecule. The empirical formula is the most boiled down version of this, reduced by the simplest whole number ratio. An example of this will be C6H12O6. This is unique to glucose. This is exactly glucose. But if we pull out the 6 out of here, we can divide it by the least common denominator and get this. This part in the middle is the empirical formula. The empirical formula could technically be applied to an infinite number of molecules, since you are basically just multiplying this by some integer. It must be an integer n. If we know the identity of the substance and we know the mass of the substance, it's possible for us to compute the empirical formula. If in this problem, I know the mass is of iron and I know the mass of oxygen. We will convert these masses to moles and using normal stoichiometry. We get our moles of iron and our moles of oxygen. We will then put them into a ratio where we will the ratio of iron to oxygen is our mole ratio here. If we divide by the smallest number, we will this will turn into a 1, and this will turn into a 1.5. Now we'll adjust it just a little bit so that these are whole numbers, and we'll get a 2 to 3 ratio. So our answer, or our empirical formula, will be Fe2O3, since there are 2 irons for every 3 oxygens. If the problem gives us a percentage, we can still apply the same method if we assume that it is a 100-gram sample. If I have 87.5% of a 100-gram sample, that means that there are 87.5 grams. So when I find the empirical formula of hydrazine, I can still take my 87.5 grams, I changed percents to grams, and convert those to moles. Then I find the moles of hydrogen, and I will follow the same step as before and apply a whole number ratio. What I will do is I will then take the moles and put them in a ratio and divide by uh, the the smallest number and get a 1 to 1.98 ratio. This will approximate to a 1. This will approximate to a 1 to 2 ratio. My answer will be NH2, um, because there is one nitrogen for every two molecules of hydrogen, or there's one nitrogen atom for every two hydrogen atoms. I'd like you to recall that a combustion reaction always has a hydrocarbon or a carbohydrate and oxygen as its reactants, and it always has carbon dioxide and water as its products. Picture shown right here. A hydrocarbon is simply something with carbon or hydrogen, carbon and hydrogen, but a carbohydrate is something with carbon, hydrogen, and oxygen, like glucose or in sugars, something like that. Combustion analysis is a way that we can actually real life way that we can determine the empirical formula, where we will take our hydrocarbon or carbohydrate, something with a compound that contains a CH or sometimes an CHO, and we will put it into our sample container right here. Then we'll close it up and we will heat it to a very high temperature. And pure oxygen will be continuously injected into this. Now, the amount of pure oxygen will not matter because the oxygen will come out the other side. And then, once it's burned, it will produce carbon dioxide and water. So we will then take our mass, we'll have a chamber here that will absorb all of the water, and then it will pass through, and we'll have another chamber that will absorb all of the carbon dioxide. We can then study the increase in mass after we burn all of our sample through and see how much water was absorbed, what mass of water was absorbed, and what mass of carbon dioxide was absorbed. Knowing how much water was absorbed will tell us how much the mass of hydrogen in our sample, since hydrogen is the only one present here and is unique to this chamber. And knowing the mass of carbon dioxide absorbed will tell us the amount of carbon that was in our sample. Here's an example of a typical combustion analysis problem. Go ahead and pause and give it a read. I'll point out some of the things that this problem specifically tells you. It does tell you that there is only carbon, hydrogen, and oxygen in our acid. That's the sample that we're analyzing. It tells you the total mass of this acid. It also tells you the mass of CO2 that's absorbed by the combustion analysis, and it tells you the mass of the water that's absorbed by the combustion analysis. It's looking for the empirical formula, and it's also looking for the molecular formula. It gave you the molar mass, and that will be important at the end. So let's find the empirical formula first. We'll have to break this up into kind of half reactions. So we're going to look at carbon first. So we're going to look at CO2. When we have our half reaction, we're just looking at carbon reacting with oxygen to form CO2. When we do this, we take our mass of CO2 and we will apply our dimensional analysis and our stoichiometry, where we'll take the known mass of CO2 and convert convert it to moles, and then I'm gonna turn the the moles of CO2 into moles of carbon. Now, what this means is that there is in this in this molecule of CO2 there is exactly one carbon. So that's where this comes from. There is one carbon in CO2. So there's 1 mole of carbon for every mole of CO2. We're looking at this part right here. Then I convert moles to grams. And that will, whenever I type it all into the calculator, that will give me 0.1367 grams of carbon. Then I'll look at the hydrogen specifically, and remember and recall that the hydrogen will react with the oxygen to form water. Now, when I start with my grams of hydrogen, I will, with my known information of hydrogen, I will convert, I'm sorry, known information of water, I'll convert grams to moles of water, and then for every mole of water, there are 2 molecules of hydrogen. So for every mole of water, there are 2 moles of hydrogen. That's where this 2 comes from. I have a 1 on bottom and a 2 here. Then I'll convert moles to grams of hydrogen. I'll type this all into the calculator. I'll take the product of the top divided by the product of the bottom and get my mass of hydrogen. Remember from the original problem where it gave us the total mass of the sample? Well, now that'll come into account because we're going to take the mass of hydrogen and the mass of carbon, which we just found, and we will now subtract it from the mass of our total sample. This is the mass of our total sample minus the mass of carbon plus the mass of hydrogen, and I get this mass of oxygen. Now I will take those 3 masses and I will individually convert them to moles. So I'll take my moles of oxygen, my grams of oxygen, and convert it to moles. And then I'll take my moles of my grams of carbon and convert it to moles. Then I'll take my grams of hydrogen and convert it to moles. The empirical formula is a ratio of these 3 moles, the mole here. So let's go ahead and put those into a ratio now. When we have our ratio of CHO, we will now find that these ratios are listed as above. I got these numbers from the previous screen where and these are the moles. Now I will divide by the lowest, by the smallest number, and which will bring me up to a ratio of 1 to 1 to 1.98. Now we can see that we can approximate to a 1 to 1 to 2, and now that means that there is 1 molecule of carbon for 1 molecule of hydrogen and 2 molecules of oxygen, giving us our answer CHO2. This is the empirical formula. Recall that the problem originally gave us a molar mass, and it also gave us a molecular formula. So now, and it also asked us to find the molecular formula. So now let's find the molecular formula. I'll have to take the empirical formula mass, which means I will take the molar mass of each one of these and add them together. So the molar mass of carbon plus the molar mass of oxygen plus 2 times the molar mass of oxygen. and I'll get a total of 45.02. It told us in the original problem that my molar mass was of the sample was 90.04. It's very handy that this turns out to be a that my molar mass divided by my empirical formula mass equals 2. This is my integer that will be applied to the empirical formula, so I will multiply every subscript in here by my answer, 2, and find my molecular formula of C2H2O4. Hey guys, thanks for watching. I know the empirical formula and combustion analysis stuff can be a little daunting, but with a little practice, we can always get it. And we'll be working on it a lot in class with a great class activity. All right, thank y'all. Say bye bye. Say bye bye. Hey, do you see yourself?